Hello, I'm Professor Steve Miller. Today I want to talk about the notes on limits of the early eddy viscosity models, which I previously discussed in this lecture series. And these are applications for boundary layer flows or external aerodynamics. But some of these things might be applied to internal aerodynamics. And some of these limitations have been overcome by more contemporary eddy viscosity one equation, two equation models. But it leads into the discussion of the necessary and early work in the late 1980s for successful Reynolds stress models. So let's look at the particular limits of the second order closure moments. And the first, of course, is stagnation flow regions, where, say, on the right here, we have a flow that comes and stagnates on a solid body, which is in green, and then flow, of course, goes around it. This is a very interesting flow, and you'll see that in these types of flows and measurements, or CFD, you'll see that terms like partial u, partial x, that's the rate of change of velocity in the x direction with respect to x, and partial v, partial y, are dominated relative to the off terms like partial u, partial y, and partial v, partial x. If you look at the production type term for these flows, p sub k, you'll see that it goes as negative u prime squared bar partial u, partial x minus u2 prime squared bar partial v, partial y, minus Reynolds stress off diagonal term u1, u2 prime bar times partial u, partial x plus partial u2, partial x1, which is the strain. So you can see and look in these stagnation regions for incompressible flows in particular that these particular terms will be balanced. And this means that these irrotational strains are going to be balanced of each other and cause a problem in terms of the model prediction. The outcome of these types of models in stagnation regions will be it'll force what would be particular three-dimensional turbulent structures to be more like two-dimensional pancakes. And this is one particular problem. And in the eddy viscosity models, the same production equation in 83 would be written as 84 here, and these normal strain terms here would be written as 2 nu t of partial u partial x squared plus 2 nu t partial v partial y squared plus nu t of partial u partial y plus partial v partial x. And this is the strain term once again, but you can see now we've replaced these front terms by 2 nu t and nu t respectively. So these terms, of course, would be balanced. And we would see in eddy viscosity model prediction study CFD that these normal strains will create excessive and increases in turbulence near stagnation regions. And so this means also that the eddy viscosity models would, say, create early reattachments and, say, a separation boundary layer. There's a boundary layer wall, and there's like a laminar bubble on it, and the flow comes back around this reattachment region right here in this separation bubble. Maybe I'll do it in green right there, is too far forward, it's too early. So that's another problem that you'll see. The reattachment region for these types of boundary layer flows will be incorrect also. Second major problem identified for external aerodynamics in the traditional models is to do with streamline curvature. So it's well known from experiments and traditional stability analysis that if you have a concave laminar flow laminar boundary layer, and here's the wall, here's the boundary layer profile, that if it's a concave shape, that the flow would be stable. If it is concave laminar flow, and here now the wall is a concave shape, like a mirror, concave mirror, the flow would be unstable and the so-called Gortler vortices form. And there's lots of information online about this. And this can be shown from the linear stability analysis too, that it's unstable, and the particular Gortler vortices form named after the researcher. It's observed in these two simple flows, convex and concave, with particular strong curvature, that is small radius of curvature, that the eddy viscosity models just aren't able to predict this unstable Gortler vortex formation and turbulence. Of course, the last major thing is three-dimensional flows, and a lot of the traditional models were formed for the boundary layer assumptions. This is really where they don't always shine, especially in complicated three-dimensional shapes and surfaces. And the most basic explanation, physical arguments why, are listed here. That in a 3D model, we would write the eddy viscosity nu t as some anisotropic tensor aij. And so that'd be negative nu t over turbulent kinetic energy times the strain tensor. And we might write it as, to try to generalize the model, as the anisotropic tensor goes as Reynolds stress tensor divided by turbulent kinetic energy minus 2/3 the Kronecker delta function, delta ij. Remember, that's 1 for I equals to j, and 0 for I not equal to j, for I equals 1 to 3, and j equals 1, 2, 3. No problem there. Here, once again, just to remember, here's the strain rate tensor. Sij is partial ui partial xj plus partial uj partial xi. And let's just look at these particular two forms of this anisotropic tensor, which is nothing but, in the first case, modeled with eddy viscosity and also written out with the full Reynolds stress tensor. So what do we really have? You'll note that nu t is, by definition of the eddy viscosity models, a positive scalar coefficient, which is typically added to the normal viscosity to make an effective viscosity. And the anisotropy in this top model here, right, will absolutely be aligned with the strain. There's no other way to do it. So aij is going as some scalar, bis k is a scalar times the strain, sij. But this is obviously not true in, the definition of aij. It sort of forces it to be perfectly aligned, but experiments show this is not the case at all when you're dealing with Sij. So what does this mean? For 3D flows, that alignment forces us to get incorrect predictions. So these are the three major observations physically that I think were made in the 1970s and 80s with the difficulties of these models, especially in the 80s. And this is when some of the new models, the differential stress models, were starting to appear and overcome some of these difficulties. And I'll talk about one particular model in my next lecture by, I think, what's normally called the HJH model, which was formed in 1995, which is a lot later. And the other way to go down is to continue with the eddy viscosity models and create more complicated models to overcome convex nature, concave nature of unstable flows, models for reattachment and transition, and models for stagnation regions. Thank you very much for your time today. I'm Professor Steve Miller.